Okay students, let's proceed. Now comes question number 3. Here you are given a square matrix of size n by n, and you have been also told that the square of this square matrix is A, that is the matrix itself, and this matrix is free from the identity 1. Then you are asked to determine the determinant of this matrix. So dear beloved ones, what you need to do here is you need to recall property of determinant. Okay, there are a lot of properties stated under the concept of determinant of a square matrix, so you need to go back and read, please. So let's directly apply that and find the solution of this. Here it is. It has been given that a squared is a, so clearly from this you can understand that a times a is a, because a squared is already a, so a times a is a squared, and this has to be called with a. And next from this, if the product makes a, remember that we can apply determinant both sides, so have det in front, again here det2. Determinant of a times a is going to be determinant of a, because if two matrices are equal, their determinant is going to be the same, right? Even though the converse may not hold true, but the direct implication holds true, right? So determinant of a times a is going to be determinant of a. Now from this, remember students, we said that the determinant of product of two matrices is nothing but it is the product of the two determinants, right? So this is the same as this one. You see students, we can write like this: determinant of a times determinant of a, and then bring this determinant of a to the left. In the case of this, you do have minus because this is at the beginning plus. So minus of determinant of a equals 0. Now, dear students, these three expressions are, you see, simply real numbers, because determinant is an association of square matrix with real number. So this is a real number. Again, this is also a real number. We do have also real number. So look, these three are real numbers. So their simplification must make equal to what? 0. And from this, what follows is this one. So let you take one of these two as a common out, and then determinant of a is going to be determinant of a minus 1 is equal to 0. And from these students, look, the product of two numbers comes 0 if either one of the two is 0, right? So either the first one must be 0 or the second must be 0 in order to have the product to be 0. So from this, either the first one must be 0 or what, students? The second must be 1, because if the second is 1, 1 minus 1 is 0, so so this is going to be 0. So either the determinant of a must be 0 or the determinant of a must be 1. So from these students, what we can obtain is, see, the determinant of the two can be either 0 or 1. So our possible answer here can be either 0 or 1. Basically, there are cases where we might have the determinant of a certain square matrix to be 1, even though it's not an identity 1, okay? So we do have these two options, either having a 0 or 1. I hope you have understood how it has been done. So proceeding to the next one, we do have question number 4. So question number 4 says that you are given this, again, square matrix, a 3 by 3 size matrix, and you are asked to find the value or the values of lambda for which this can be invertible. As students, you need to know about what property of invertible matrices. We know that for a given square matrix A, you see, the matrix A is said to be non-singular or invertible if its determinant is free from 0, right? So if the determinant comes 0, it is said to be what? Non-invertible, or it is said to be singular matrix. But now you have been told that, you see, this is an invertible matrix. It is a non-singular matrix. So indirectly, we know that this determinant is different from 0. So we are now going to calculate the determinant of this and look for the case where lambda is going to be a number that makes our determinant different from 0. So let's see how I'm going to do. Here it is. For a matrix to be invertible, the determinant of A has to be different from 0. So the governing one for this discussion at this point, okay? So now let's directly calculate the determinant of this one. So now look, students, when I calculate the determinant of this one, look, I do have different options. Basically, I do have 9 different options I can use. You see, I can use either columns or rows, as you see. So I do have 3 rows and I do have 3 columns, so I do have 6 different options, so I can use 6 different options in order to find this determinant. But whenever you do so, try to think of the case where you might have a lot of zeros, okay? Try to think of that case. So how are you going to find the case where you can have a lot of zeros, students? Look here, students. Now look, in the case of this, you can choose the second row. You see, students, if you choose the second row here, you see, students, if you choose the second row here, what you can have is what you can obtain is the determinant in a simple way, because in the second row there are 2 zeros. You might also choose the second column, students. This is also another option. But what I did here is using second row expansion, I can obtain the determinant of this one, right? So as you know, this is plus and this one is minus, and this is plus and this is minus and this is plus. I'm saying plus because this element is the intersection of the second row and the second column. So the second row and the second column do have subscripts 2, 2, so the sum of 2 plus 2 makes 4, and minus 1 the power of 4 or even is positive 1. It is for this sake that you see we need to use plus here. So using this, now I can using the second row I can determine the determinant. How is that done? Forget about this one, because 0 times any sort of determinant is 0, and again forget about this because 0 times any determinant is going to be 0. So when you come to this, this is basically plus, so you will take lambda plus 2 as it is, as you see here. And now try to cover the row where lambda plus 2 is going to be located. So you need to cover the second row, and the column where lambda plus 2 is going to be obtained, it is the second column. So as you are covering the second row and the second column, you are left with these entries of your matrix A. Lambda minus 3 as you see, and 3 as you see here, minus 5 again comes here, and lambda plus 5 follows. So now we need to find the minor for this lambda plus 2, and that is the determinant of this square matrix, 2 by 2 square matrix. So we are now left with, you see, students, equating this one with a number different from 0. So this is going to be lambda plus 2 times the determinant of this matrix. This can be done in a simple way. As you see, this is lambda plus 2. So lambda minus 3 times lambda plus 5 is going to come minus 3 times minus 5 is minus 15. So minus 15 makes plus 15, right? So further simplification of this make this lambda plus 2. This is lambda squared, and 5 lambda minus 3 lambda makes 2 lambda, as you see, and minus 3 with 5 makes minus 15, so plus 15 goes 0, so we are left with this alone. So here again we can further simplify. Lambda can be taken as a common, so look, lambda is taken out, so lambda plus 2, this repeated binomial expression is going to come. So our intention is to obtain a case where this determinant of matrix is different from 0, because it has been said that this is invertible. So we have to look for values of lambda where this can't be equal to 0. Okay, that's why here I use a not equivalent sign. Okay, so try to think of values of lambda where this cannot be 0. And in the case of this, all real numbers can be used except 0 and minus 2. Okay, because if you are using 0 and minus 2, everything goes 0. So you are free to take any real number except 0 and minus 2. So here you can put lambda different from 0 and lambda different from minus 2, just to say that any real number can be used except these two, or you may also write the set of all real number without, you see, the set containing these two, 0 and minus 2. I hope you have understood. So whatever, you see, lambda values you may use here in place of this lambda matrix, lambda of this matrix, except these two, except 0 and minus 2, this will be invertible, okay? But if you are using 0 and minus 2 in place of lambda, you see one of the two, it will be non-invertible matrix. If you are using 0, it will be non-invertible, and again if you are using minus 2 there in place of lambda, it will be again non-invertible matrix. I hope you have understood. So proceeding to the next one, so here it is, the set of all real number except these two. So proceeding to the next one, we have question number 5. So for this particular question number 5, we do have one question, and that is to determine the value of what, student? The value of a and b. The value of a and b here. So your function is a piecewise function. It has been defined this way. So if it is continuous on the set of real number, then you are asked to find a and b. Okay, you are asked to find a and b. So how is this can be done? So simple. What you need to do is you need to bring the concept of continuity here. So as you know, a function f is said to be continuous at 3 if the limit exists, and moreover the limit of the function as x approaches 3 from the right and from the left is equivalent to f of 3, right? So the limit comes as it is, but as you are approaching to 3 from the left, which of these three shall you use? Approaching 3 from the left, you see, requires the second one, because as you are approaching to 3 from the left, you are using numbers like 2.9, something like that, and these numbers are here, you see, so you need to use ax plus b. And f at 3, exactly at 3 is, you see here, minus 2, because when x is 3, you see, equivalent sign here is used, minus 2 is going to come. So from this, 3a plus b equals minus 2 can come, because you can directly put 3 in place of x. So you do have 3a plus b equals 2 f of 3. F of 3 is already known, it's minus 2. So you are having this. So as can be shown here, we have assured existence of limit as well as left side continuity by using this concept. Now comes for this function to be continuous, let's consider the case of continuity to the right of minus 1. So the limit of f of x as x approaching to minus 1 from the right needs to be the same as f of minus 1, because for this to be continuous throughout, the function has been split into 3 at 2 different values, at minus 1 and 3. So we have to create a case of continuity at these two broken values at minus 1 and 3. So when you come to the selection of this function from the right of minus 1, you're now going to take number 2, because this is your function value for values less than minus 1. But as you come to the second one for values greater than minus 1 from the right, you're going to consider your function ax plus b. So you have that one, ax plus b here, as x approaching minus 1 from the right. And this f of minus 1 is nothing but it is the case where f is going to be when x is exactly equal to minus 1. So you need to use this one, it is 2 as you see. So can we directly put minus 1 here in place of x? Possible, because nothing makes undefined here. So this turns to be minus a plus b, right? Minus a plus b is equal to 2. Now, dear students, we have obtained two unknowns with two equations. So this can be solvable, right? We can directly subtract 3a minus a, it will be 4a, b minus b 0, and minus 2 minus 2 minus 4. So the value of a is going to be minus 1, clearly. We can obtain that to be minus 1. And once we know what a is, we can determine b, just substitute in one of these two. And we know that b is minus 2, or minus 3a, or b is 2, you can move this one to the right, 2 plus a. So 2 minus 1, because a is already known as minus 1, it will be 1. So the value of b is 1. So if a and b are, you see, minus 1 and 1, this function is continuous at any real number, right? I hope you have understood in a better way, right? These two.